Okay, so this is joint work that I will present, and it's joint work with Alexandru Balta, who you know and who's here. And I will talk about correlated information, a logic for multi-partite complex systems. Right? So what are the main ideas? Our aim is to investigate the relation that you have between what I call qualitative information carried by parts of a composite system and the information that's carried by the whole system. And the claim is that the non-classicality of a physical system, or the existence of so-called non-classical correlations, is informationally characterized by the fact that this information is carried, that what is carried by the system is more than the sum than what's carried by all the parts. Right? And what we have as a proposal is kind of a new logical system to reason on an abstract level and on a more generalized level about the qualitative information and these correlations in systems that are composed of subsystems and of parts. Okay. Now, to do this, we use a tool that's known by logicians as epistemic logic. So we reason about information localized in parts of a distributed system using this epistemic logic. And epistemic logic is a type of spatial logic. And I will tell you more about epistemic logic since I don't assume that everybody will know this. So, and in particular, we will use something that we call group epistemic logic, which means that I will have epistemic model operators for what I call agents, individual agents. And you can think of individual agents as basic parts of a system, components, elementary subsystems, locations, qubits, right? So if I talk about agents, you think about qubits or whatever. That's fine, I will talk about agents. And I will talk about groups of agents, or compound subsystems. And now, of course, epistemic logic refers to episteme or to knowledge, but if I talk about knowledge, this means really the information that is carried or that's in principle available at a location or at a subsystem. Right? And you can actually associate each part of a system as a virtual agent. Think of this agent as what this agent can perform. This virtual agent can perform some observation at a certain location. Okay? That's how I'm thinking of it. So my notation, so I have a set n of labels for basic components. I have subsets of n for as a notation for complex subsystems or groups of agents. My notation n will indicate the largest group, which is the whole world, and I have singletons of agents, which are just the individual components. I will have epistemic operators, as I said, but now, so I will have operators ki, sub I, for every subsystem I. And this will give me a logic to reason about, indeed, systems composed of subsystems. Right? And I'm reading ki phi as a system or groups of agents I carries the information that phi. Right? So how does the logic look like? Well, actually, I just have classical propositional logic. So this part is just classical. I have basic atomic sentences given from some set of basic facts that you have to start with. I have classical negation, classical conjunction, and then I have my ki phi operator, which is a model operator for groups of agents. For every subset of systems, for every subsystem, I have a ki operator. Right? So that's what we call general epistemic logic. Now the semantics for this is given in a Kripke semantic setting by what we call a Kripke frame. Right? And that Kripke frame consists of a set of states sigma together with a bunch of relations. And these relations are labeled by subsystems and are equivalence relations. So here S equivalent to S prime means that the states are observationally equivalent or indistinguishable for subsystem or for system I. The second condition says that information is monotonic with respect to groups. So if I is a subgroup of J, then the relation for J is included in the one for I. And I have a kind of observability condition which says that from the point of view of the whole system N, and any two states that are related in this way are the same. Which means that we identify states of the worlds that differ in ways that are not observable by the whole world. Right? So this is a very simple type of frame semantics that we have for our logic. And you can use that, of course, to give the semantics also to the propositional part, the classical propositional part. And the important thing is I give the semantics to the KI operator using this observational equivalence relation. So here in a given state S, the system carries the information that P, so KIP is true in state S, if and only if P holds in all states of the world that are observationally equivalent to S. Right? So that's exactly what it says. And now when you have the semantics, you can also look at the proof system, and we claim that it's easy to see that you can build easily a complete proof system for these general epistemic frames as the semantics for it. And so in addition to all the classical propositional tautologies, I'm just going to encode frame conditions now in the proof theoretic setting. So I have the first axiom is Kripke's distribution axiom, which assesses this Ki distributes over the classical implication. Truthfulness, positive and negative introspection, they encode my equivalence relation on the frame setting, right? So flexibility, transitivity, symmetry. I have monotonicity of group information that also encodes the other, and observability. So P implies K and P. So this just encodes all the conditions that have in the frame, and then you can easily see that indeed then, if that's the case, you will have a complete proof system. And I have, of course, an inference rule, the classical inference rule of model exponents and substitution. And as for normal model logics, we also have like a Ki necessitation rule, which means that if phi is always true tautology, then Ki phi is also true. Okay, so now I will tell you a little bit more about the frames that we have. So given a general epistemic frame, we can construct the notion of an I local state for a subsystem I, and that will just, my notation is S sub I for that, and that just gives you the equivalence class with respect to this observability relation that I have, right? So below you see that my notation here, this means that the local states Si and Si prime are exactly the same, right? Now an important question that we ask is what exactly now is this information that is carried by a composite system? Right? I want to look at this operator more in particular, Ki, K sub I. So what is the implicit knowledge of a group? What can a group come to know? And one possible answer that we'll find in the literature, and that's well known, is distributed knowledge. There's a book of Fagan, Halperin, Moses and Vardy, in which they discuss this as the natural candidate for group knowledge. Now, what's this distributed knowledge do? Distributed knowledge can be defined as a distributed observational equivalence relation, which is just given by the intersection of the individual equivalence relations. Right? So you define a new relation as the intersection of the individual ones. And the idea here is that two states are indistinguishable for a group if they are indistinguishable for all the members of the group. And of course, if you define this new relation, you also have a new modality that you have, which is then exactly true when this relation holds. And the model operator for distributed knowledge is then denoted as dki sub I. Now, indeed, so Halperin and these guys, they identify the implicit knowledge of a group I, so Tingoma subsystem, with distributed knowledge, dk sub I, right? And we are wondering, is this really the correct notion that you really want in all cases? Because if you think back at my virtual agents, So implicit knowledge or information was explained as what an agent or group could come to know based on potential observations. Now, but what are these observational capabilities of a group? So using the intersection of individual observational equivalences makes sense only if you assume that a group's observation are nothing more than the observation of either of the members of the group. And we think this is highly unreasonable, but it's an unreasonable assumption because, I mean, it excludes the fact that you can have like joint observations where agents are correlating the results, right? And that's why we think a more natural notion for group information or group knowledge would be something that captures correlated knowledge. Something that, what you could come to know by performing joint observations and sharing the results. And you can think in similar terms in physics, right? You have this physical system. Given a physical system, I carrying some information. Can we learn this information by just putting together the pieces of information of every component? And of course, we all know that in the classical case, the answer is yes. And in the quantum case, this is not true. I mean, the whole is not the sum of the parts. So this we know. Now, we want to capture exactly that distinction in our general epistemic logic, right? So we want to make this very explicit on the logical level. So, given my setting of a general epistemic logic, I will tell you what the notion of separability is and how we encode it. So, for J subsystem of I, we say that the system I is J separable in a state S if Si can be written in the J part and the I minus J part. It's fully separable if you can write it for every subcomponent I in I. Okay? So fully separability means that the group I's knowledge in state S is the same as the distributed knowledge. Right? Now if you have that, then you can say that the general epistemic frame is classical. But first I have to say that the state S is fully separable if for every subsystem I it is fully separable in the state S. And then I can say that the general epistemic frame is classical, of course, if all its states are fully separable. So if it satisfies this, which means that group knowledge would be equal to distributed knowledge. Right? And of course, I mean, in the quantum case this will not hold. For instance, entangled information is not going to be distributed knowledge. Take for instance the Bell state, the one that I've given here, and then I'm identifying my virtual agents, and I call them Alice and Bob at each of the locations. So Alice and Bob can do local observations at their own qubits. Alice will know that after many observations on identical pairs that she has from the beginning, that there is a 50% probability to get a certain answer, and similar for Bob, right? So 50% probability that she C1. Now notice that these observers, if they would share all the final results of all their observations, at the end, they will never find out what the rule is that correlates exactly the information as in the Bell state. Because if they just share their final information, they could exactly assume that the correlation was the opposite one. Right? So what you need is on an abstract logical setting to characterize exactly that you get this Bell state. You want that one and not that. So the idea is that they can find out this rule by performing joint observations, exchanging the result after every individual observation. Oops. Now, first we look back a little bit at the classical case. In the classical case, the local state Si of any system I is reducible indeed to the local states of its components, right? So, actually every classical epistemic frame can be canonically embedded in the Cartesian product of the state spaces which are given by the local states. And that's exactly what is known in the literature as the integrated system semantics of Halpern and these guys, right? So, and this is also known as the S5 critical models, where you just have this embedded into the Cartesian product of the local state spaces. Now in the quantum case, we know of course that the quantum system composed of n subsystems cannot be embedded in the Cartesian product of the local state spaces. It is represented via the product, tensor product. So indeed, when S is entangled, it cannot be decomposed as a tuple of local states. But composite quantum systems can be structured, but of course not as classical ones, but as non-classical epistemic frames. And I'm just taking the same conditions as I had before, but now saying that they can be structured in a natural way. First I'm going to define what I call an I state, which is the state of subsystem I in a global state S, by putting S sub I as this, where of course rho S is the density operator associated to S, and this is my partial trace operator with respect to the I's environment n minus I. And then of course I have an I state of a quantum system. Then I can define, I'm telling you what my indistinguishability relation means in this case, right? So remember my general epistemic frame with indistinguishability relation. So here it just means that these trace operators have to be the same. So the I states for these subsystems have to be the same. And this structures the tensor space as a general epistemic frame. Now this definition of the I state that I have is a standard one in quantum mechanics for the state of an entangled subsystem I. Indeed, this encodes the information carried by subsystem I of a global system in a state S. Now, there is a way to justify this more intuitively, well, and also very clearly justify this as observational equivalence if you think about it of doing local quantum measurements as observations, right? So I'm now going to look again at this observational equivalence relation using local measurements. So provide again, think that you have an unlimited supply of I entangled systems in the same entangled, of course, global state S. And then you can do all possible I local tests, local measurements, and observe if they succeed, provide the answer yes, or if they fail and they give you the answer no. And then you can repeat the same test on different copies of the same thing. And then of course you write down the frequency of the answers. And then after many tests you can approximate the probability to get a yes or no answer for each local test that you're doing. And then, so this gives us a relational view of this I equivalence that I have for, in the quantum case, for my general epistemic frame. So, I can say that two states S and S prime are I equivalent if they behave in the same way under I local tests, which means that the probability to obtain a yes answer to any local test in the two systems is going to be the same. Right? In other words, quantum mechanics tells me that the mixed states are the same. Now, you can write this out as a nice theorem, in the sense of saying, okay, I had the ones with the trace operators on the one hand, and I have this one, and they're just going to be equivalent. Okay? I didn't do that also. And the idea now is that you can use this, and we know that this equivalence relation is giving me the interpretation for the KI operators. So now you can use this setting to give an informational characterization of separation and entanglement. So two systems are, we know that, two systems are entangled if and only if they potentially carry non-trivial information about each other's information without any communication, right? So how to encode that in my setting with my KI operators? So first you choose any fully separable state, and I call it W. And for instance, you can take 0 tensor 0 if you want. Then two subsystems I and J are entangled in the global state S, if and only if S satisfies this. So my logic, that means that Ki knows that J knows that the global state is not the fully separable one. So that's a way to encode exactly what entanglement is in this setting, right? And separation would then be the classical negation of this. So that gives me an informational characterization using my logic of entanglement. Now our examples can be modeled more accurately if we add structure to our crypto frames. So in order to capture really the observational capabilities, think of my virtual agents with observational capabilities of looking what's the information at that certain spot. So you can do that more explicitly if you add a little bit more structure to my epistemic frames. So I have three types of structures I'm going to tell you about, and the first one are just relational models, right? And these relational models consist of states, and states now are going to be relations between an agent's observation. So given sets O1 to On of possible observations of each agent, a joint observation will be a tuple of observations in this O1 cross to On. So a state of the world now can be characterized by these joint observations that can be performed on it. And so a state is going to be a set of such tuples. It's a relation, right? So a model has as a state space S inside the power set. And then a local state, of course, S sub I, is given by the projection onto the I part. So you project onto the I part of that. And then observational equivalence is given in the same way as you take just the SI's have to be equal for, well, S and T in this case. So that's the first setting that I have. Now this can be generalized a little bit into a second type of models, which we call multiset models. So instead of sets of tuples of observation, now we're going to consider multisets. So agents now may record how many ones that they see. Alice can record how many times she's seeing a one, right? And you want to code that explicitly. So to do that, we don't just need the relational models, we need to say exactly these numbers. So now states are going to be multisets of joint observations, which means functions as from tuples of observations into natural numbers. And again, the local state here for system I will be given by this projector, but which gives me then a number, and then I'm summing up the numbers there. Since states now are going to be functions from tuples of observations into natural numbers, and for local states, I just take the I part. Okay. Right? Since a local state is just like a state for a certain subsystem I, and so I have to restrict to the I part. For correlation models, so I'm now not only just saying like how many times I'm seeing a certain outcome I, now I'm just saying, well, I'm going to generalize this into any type of result that you want to have. Call it observational result, right? Abstract something. So this means that together with a set R of possible observational results, I'm going to have an operation on that, an operation of composing results. And this operation may be partial, only defined for a subset A of R, but it has to satisfy the sum condition of composing results whenever these A K's are pairwise disjoint. So that's just to encode indeed that this operation on abstract results does what I want it to do. And I call R sigma a result structure. Right? Now what the correlation model is going to be, given such a result structure and a tuple of sets of possible observations, a correlation model over this is given by a set of maps of S, where S is a function of this into R. So not anymore into the natural numbers as in my previous one, in my multiset models. Now I'm just generalizing this into my result structure. So for any, well, natural numbers are going to be special case of R. Right? So global states will be functions of tuples of observations into R. And similar for local states, but now, of course, sigma is not going to be normal addition, but it's my operation of the result structure that I have. And then correlation models are, of course, general epistemic models. So take the observational equivalence to be the identity of the corresponding local states. And necessarily, these correlation models are not necessarily classical epistemic frames, right? Group information is not necessarily distributed knowledge in this case. Examples of correlation models. So, relation models, the first ones that I had, you can take R just as 0 and 1. Okay, and this junction is the composition in that case. The multiset models, R is going to be the natural numbers, and addition is the composition in that case. And for quantum models, for instance, the correlations, so with sets of observations OI are given by the Hilbert spaces. Joint observations are going to be interpreted as projectors onto the corresponding state, if you want. The result structure is the interval, for instance, now 0 and 1 with normalized addition. And the result of a joint observation, OI, made in a state S is interpreted as the probability that some outcome of a local measurement will be O, for instance, right? And now, so for these correlation models, my general epistemic frames for these correlation models, I can, of course, in this case, also have a logical language and a nice logical setting. So what you have to do now, because we have more expressive power with these observational results, you extend the logic, general epistemic logic that I had before with my ki operator, and I add this as an operator, which says observation O subsystem I are taking results R. Right? And the interpretation of this, so the semantics for this proposition is exactly given by my map Si for the I part, which has to give the result R. Now the last slide, I have 2 more slides, is, well, you can give nice examples of axioms that you have for this O proposition. For instance, you want to say that observations have unique results. So for 2 results are different from P, you want that if an observation takes result R, then it's not so that the same observation will have result P. So you have negation of OPI. The second one, which would also be naturally to assume in this case, is groups know their own results of their own observations. So OR for subsystem I will imply that at that subsystem, that's the information that's stored there. So KI, ORI. And then the last one would be group knowledge is indeed correlated knowledge, which is based on joint observations. That was the whole group, right? So, well, it's at the bottom of the slide. If phi is the information stored in subsystem I, so ki phi is the case, and I also have a bunch of observations that give me result R, then that implies, and that is actually a universal modality which allows me to jump to any other state. So k empty set there is the k operator that gives me in any other state with the same observation, with the same results. I know that phi has to be true, right? Because I had ki phi before in a state with the same observation and the same result, which allows me to jump to any other state where then phi has to be true. So, and that's the final slide that I have. So for every finite set N of agents, systems, every finite result structure, and every total of finite observation sets, there exists a complete axiomatization of this given logic in the last slides with respect to correlation models. So, and the axioms that I saw on the previous slide are 3 of those axioms, and I think, correct, Alexander, we just need 1 or 2 more. One more, right? Two. Okay. Okay, stop here. So, questions? Okay.
First of all, I want to say how much I like this talk. It's really wonderful. People like Rob van der Meijden and also Ellie and me tried to formulate epistemic logics for quantum logic, and I don't think we came anywhere close to something as nice as this. Having said that, I have some confusion in my mind about what it means for an agent to know something. And according to one of your models, it was basically equality of density matrices. Yeah. So in teleportation, there's a curious thing happening, which is that, let's say Alice has a state which she wants to teleport to Bob. When she has it, she knows its state, according to your model. And after she's teleported it, not only does she not know it anymore, but she doesn't even know it in a timestamp sense. So is this feasible interpretation of your model?
No, because well, you're talking about like okay, so the traditional teleportation scheme, you really have Alice, and when you're talking about this, what Alice as an external observer knows about the qubit that is there. Actually, the whole point is that she wants to teleport something about which she possibly doesn't know the state.
Right, but your semantics would say since she has the state, she knows it.
Yeah, but the thing is that I'm only talking about the qubit, so Alice is completely not in the schema. And the qubit knows its own state. The qubit itself can look at itself. So this is about just the subsystem, the information and the subsystem. If you want to, so I also looked at your paper with Ali at some point, and there what you do is you take external observers and what they know, right? And that is not going.
I see.
This is not the same as information that is.
Yeah. I understand.
Yeah.
If I may, I think actually that what Ranash said is literally true. It's just it's odd. But you said that after the qubit is teleported, according to this logic, Alice, whoever it is, which means the qubit of Alice, doesn't know it anymore. And that's correct because all it knows.
Not even in a time sense.
Yeah. Because what's there actually after that is nothing to do with the qubit that has been teleported. It's actually the part of the dust. So essentially there is no more relevant information about it to be left. So instead, both knows.
So I'm going to say something even stronger than that,
Yeah.
which is she doesn't even know that some time ago, before I did the teleportation, this is what it
Yes,
was.
exactly. And this is and this has to do with the fact that at least the standard representation which you are using of the states in quantum mechanics doesn't have a memory. So once you apply, say, unitary or whatever, unless you store that unitary somewhere else, the state itself, the state itself doesn't tell you what was before, what was the past. So if you add a history or a memory, then you have this.
I think I'm asking something which might be related. I don't see what's happened to the classical information in this framework, because sometimes teleportation that Akash is saying is one example, but like there are protocols that when you want to analyze their security or the information of the knowledge, you need to have both classical and quantum, because I might prepare a quantum ensemble and give it to Bob. So Bob will, as long as it doesn't have the extra classical information on the top, will think that this is totally mixed state. But if I give the classical information, then you know which of the ensemble I prepare suddenly become total information. So it seems that, I don't know if I missed some part of it, is there any way that we can look at the classical and quantum at the same framework, and they might even relate it to each other? The classical distribution will give some knowledge about the quantum distribution, and the quantum distribution gives something about the classical.
Well, I think the whole setting of these general epistemic frames also includes the classical part.
Yeah, but you're doing it separately. The point is that in some of the protocol you need to, this classical, I don't want to have the classical knowledge to be analyzed separately and the quantum knowledge analyzed separately, because the classical knowledge gives me something about my quantum knowledge. An observation of my quantum knowledge gives me something about the classical one.
But the classical one is in here if you can just write the sub A as the distributed knowledge, right? So inseparable state will be the classical one.
No, but we have an extension that does, but we don't have continuous flow, that does more what you want. I mean, if you have both of them, yeah. I mean, both real agents, the classical agents, and this kind of quantum information.
Yeah, but she's not even talking about the real agents.
Well, no,
No,
just,
and pure classical information, which is there.
Maybe this is a good point to say we should talk further over lunch, since we are already well into the lunch break at this point. Let's thank all our speakers in the